All right. So remember that the last time we spent a long time thinking about the random walk. We started out thinking about the random walk on a lattice. We said let this lattice spacing be A. Let's assume that our random walker hopped either to the left or right by unit distance A over a time tau. So I had some stop clock which was ticking in units of tau, and it hopped to the right or left. And then my question was, suppose I started either at the origin or at some random point. For simplicity, let me just make that the origin. What is the probability of being at some other point at some later time? So this goes off to infinity. And then we said that look, at t equal to 0, I'm definitely here. As time goes on, I would move from being here to maybe some probability of it being here, etc. And as I went on in time, this would sort of become, there'd be non-zero probability of finding it further and further and further away. And because all of these numbers must add to 1, this thing would sort of decrease correspondingly. So if I plotted that, if I sort of imagine that, look, I'm going to wait a really long time and I'm going to take this A going to be very small, then in the beginning, I'm very sharply localized here. And as time goes on, I get a probability distribution that looks more and more like this. Given that I've said I started at the origin, we derived some properties of this probability distribution. We said, look at the number of right steps minus the number of left steps. Call this the displacement delta. And then we can ask, what is the average value of delta? What is the fluctuation in delta about that average value? So technically, this object should be delta squared averaged minus delta average squared, which is the same thing as taking the average of delta minus the average value of delta, squaring it, and then taking the average. This is with respect to the mean value. How am I spreading out? So here the mean value was always at 0. If the walk was symmetric with p equal to q equal to 1/2. And as time went on, it just got broader and broader and broader. So then we did this explicitly. We took some time and we did this explicitly in the case of one dimension. And then we said that the average value of delta was just n, so average value of the number of right steps was just n times p, which is n by 2 in the case of hopping to the right or to the left with equal probability. So the average value of delta, which is the average value of number of right steps minus number of left steps, was just 0. So on average, I wasn't going anywhere. But the important thing was the fluctuation. So if I looked at delta squared average, this I found out was equal to n. And because this is the length scale, I should have a factor of a squared there. I may have put it in, I didn't. If I interpret this as a length, if I sort of remember that the unit in which I'm hopping is a unit a, then I should have an a squared here because n has no dimension, but this has a dimension of a length squared. So it's useful to remember these dimensional arguments because then you can reconstruct it and put it back at some later point.
So when the distribution becomes continuous, how will we measure a actually, the step size here?
So in this way, it's sort of harder to do it. It's just sort of, I'm inferring this answer saying this has to have the dimensions of length square, so I'm putting this in here. But the right way to go to the continuum limit is what we did after that. We said let us start with saying, suppose I have some point x here, and in general this is some lattice with some lattice spacing a here, and I imagined all the steps in which I could get from here to here in some time step tau. And then we said I can only get here if at the previous time I must have been either here or here or here or here, the way I hopped. And then I said let me take the limit in which a was very small and tau was very small. Okay, so that was one thing that we did. We said when we look at these, we want to look at quantity like the probability of this being exactly at x at time t given 0, 0, started at 0 at time 0. Then, but the whole idea was not to represent it explicitly like a lattice, but to try to take the continuum limit. So from the lattice, which is how we originally formulated it, we wanted to go to the continuum limit. So what we did was describe a way to do that. So let me just mention one more thing, which again is just sort of mathematical preliminary, which is straightforward. But suppose I have some function that I define only on, say, some closely spaced set of points. So my function might be here, 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 something like that, let us say. Might look like that. Now, as I imagine the spacing becoming smaller and smaller, and for example, time becoming larger and larger, this begins to look like a function that is a continuous function, provided I don't look at these points in great detail. I don't actually see that there's one point, there's a separate discrete point, a separate discrete point. I can just sort of fill it in like this. And then when I talk about the continuum, it's clear that I shouldn't be asking the question, what exactly is the value that it has at this spatial point x? Because maybe that answer is correct when I talk about a lattice when x is precisely this point, but I'm not sure what it means when it's exactly here. I don't have a clear definition of what that is. So what we ask, the sort of question that we ask is, let us think of some probability density p of x. Let me multiply this by a small element d of x, and this quantity has a right interpretation. So this quantity is a probability. And this here would be called a probability density. So over here we talked about probabilities, but when we go to the continuum limit, the smooth limit, we have to talk, instead of probabilities, we always have to talk about probability densities, because probabilities don't make sense as it is. You must take a density multiplied by a very small region. So that answers the question of what is the probability of being somewhere between x and dx. So if this point is x, this point is x plus dx, this is the probability of being somewhere in between that. As I make dx small and small, the probability goes to 0, as it should, because as I said, the question of where is it exactly doesn't really make sense. But in terms of probability, this makes sense if I think of a continuous function, and this definition certainly makes sense. So if you remember, we took the p here, and then we made it a sort of, we divided by a to the power d, and then made it a quantity p. So this was p at x and t, and this is small p at x and t. So now this was our probability densities. So this essentially, by dividing it by the small a to the d, which I will take to the 0, I will say that if I multiply this by the a to the d, which is my little dx, then I will get back the original probability, which is what I wanted to do. I'm just stressing this because one would normally go fast over this, but I don't want this to be a confusion. Whenever we talk about things in the continuum, whenever we try to understand that, then we will choose densities rather than probability values themselves. So if you go back to the calculation that we did and reconstruct it, we essentially calculated p of x comma t given 0 comma 0. We subtracted from this p of x comma t minus tau given 0 comma 0. We divided by a small tau, and then we took the limit in which tau went to 0. And this we identified with delta p of x comma t by delta t. So this is a sort of usual way in which you take from a discrete set, you take a continuum limit by precisely through definitions of this sort. You divide by tau, take tau small, and then you look at the limit of this. This coincides with this object. The other thing that we did was look at the limit of, say I'm going to write it only in the x. So p of x plus a plus p of x minus a minus twice p at x divided by a squared, taking the limit, sorry, I already have a limit, taking the limit at a going to 0, this object here became delta squared p of x comma t by delta x squared. This is how you would write the second derivative. This is natural to us. This is in the continuum. This is x, suppose I'm at x, this is x plus a, this is x minus a. I want to take the limit in which these points become very close to each other. So in that limit, this particular definition gives you the second derivative. Once I do that, I have the diffusion equation, which is delta of p of x comma t divided by delta t is diffusion constant d times delta squared by delta x squared p of x comma t. So this would be the one-dimensional diffusion equation. In more generally, I would have delta p by delta t, p of x comma t equal to d times this quantity del squared of p of x comma t, where del squared is defined as delta squared by delta x squared plus delta squared by delta y squared plus delta squared by delta z squared acting upon something. So this is an operator which acts on P.
So still the diffusion constant is having the terms like A and tau, right?
So in here the diffusion constant d, the way we defined it was as I think 1 a squared divided by twice the dimension d times tau. So this is how we took this limit. We said that in order to have a finite value of the diffusion constant, we must send a to 0, tau to 0 in such a way as to keep this quantity finite. Dimension d anyway is between is 1 or 2 or 3 depending on how it is. But these other quantities we have to take to 0. So this you have to do somewhat delicately, because it just says you must take it to 0 but in such a way that a squared divided by tau goes to a constant. Is that clear? So now we have an equation that looks like this. This is called a diffusion equation, and the interpretation of P of x comma t is that if I take P of x and t, multiply it by a small element dx, this gives me the probability of finding the diffusing particle in a small interval dx about x at time t. That's exactly what we're doing. Okay, good. So now let's now make one more step. That is to go from the probability of finding a single particle at location x at time t to a density of particles at location x at time t. Probability of finding the diffusing particle in a small interval dx about x at time t. So that is essentially a function that looks like this, and I have to try and understand it. I'm saying that function solves this particular equation. So here this is one dimension. So I said this is a completely, this only involves x, there is no vector sign here. So if I take the solution of this equation, multiply that P of xt by dx, that gives me the answer to the question of what is the probability of finding the particle in some little interval dx about a point x. So I can say, given suppose that function looks like this, what's the probability of finding the particle in a small little interval between say 20 and 20.001? That's a question I could ask. And I can, the way I ask it is to essentially calculate P of x and t, substitute x equal to somewhere in the midpoint of 20 and 20.001, multiply by that width, which is 0.001, and that will give me an approximation. Technically speaking, this width has to be taken to 0 because it's only in that mathematical limit that is correct. But approximately speaking, there should be a reasonable answer, provided the distance between 20 and 20.001 is not too much. Okay? All right. So now what I'm doing here is, instead of saying that, look, I'm just looking at one particle and where it's going either to the left or right, I imagine I have a large number of particles and they could either be moving here left or right. And then my question is, what is the density of those particles at some point x at time t? That's really the same question, because that density is proportional to the total number times the probability of finding it there, times that this particular probability density. Okay. So I can interpret this either as the probability of finding one particular particle at point x at time t, or I can say, suppose I have a large number of particles, this is proportional to the density of particles in a neighborhood of x at time t. Is that clear? So now this equation I can write in terms of that, and this is the notation I will be using from now on, that delta of rho as a function of vector x at time t divided by t. This is how that density changes. This changes by an amount which is diffusion constant times this operator del squared acting upon rho at x comma t. And diffusion equations are normally written for densities. So remember that suppose I have all my particles in in some box, let me say. I have them walking around here, and I say, what is the total density? This is the integral over the full box dx, the density at every point x at time t, and because nothing leaves this box, this number must be a constant. This is just the total number of diffusing particles or the number of particles inside that. So I'm just taking these words and converting them into an equation that has this particular form that you can look at. All right. So this says that the number of particles in the box is conserved. That is to say, this quantity on the right hand side doesn't depend upon t, even though t enters here. So technically speaking, whatever I did after I integrated over the x should still depend upon t. But if I choose this box size to be the whole box and I say no particle can leave the box, adding up the total density inside this box, summing it up or integrating it in this language, is just gives me the total number which cannot change in time. We are taking the actual density of particles and saying that the probability density of finding one particular particle is like taking a large number of particles which are independent of each other, letting them walk around, and interpreting the probability density as n times, interpreting the number density as n times the probability density. Okay, let me just show you how that works. Suppose I'm essentially saying that I interpret the number of the density of particles as rho of x and t, and this is just n times the probability of x comma t. This is just my interpretation of the thing. To instead of talking about only one particle, I can now talk about n independent particles. So now look at how this works. Now if I integrate over x dx rho of x comma t equal to n integral p of x comma t dx. Now this quantity is 1 because it's a probability. So it must add up to 1. So what I have on the right hand side is n. That means this is the density of particles, because if I integrate this overall, the whole volume, I have the number of particles in that volume. Okay, so that's all I'm saying. It's just a change, a minor change in language. Now we are going to explore some different ways of writing that same equation, but let's just sort of do it slowly in steps. First of all, I again want to review a little bit of basic mathematical background. None of it is very complicated, but let me just first of all remind you of the distinction between scalars and vectors. A scalar is a quantity with a magnitude but no direction. Whereas a vector is a quantity with both a magnitude and a direction. For example, a quantity with a magnitude but no direction is something like a speed or a density. Whereas a quantity with magnitude and direction would be like an electric field or a velocity. Okay. So here, for example, you might say the density at a point is 23. That has no direction associated with it. Saying this car outside IMSC is moving with a speed of 20 kilometers an hour. That again is a quantity that has no direction. Over here, on the other hand, you can say the electric field here points in the direction of the door, because if I put a little charge there, the charge is pushed towards the door. Or I can say the car in front of IMSC was moving towards the main road at a speed of 20 kilometers per hour. In which case I have given it a direction, I have said it's moving in this particular direction, whereas earlier you did not have that information. Okay. Now these quantities such as rho of x and t are what are called scalar fields. A scalar field is just a scalar that is defined at every point in space. Okay? A vector field is a vector defined at every point in space. We won't get into any more details than that because we won't need it. Again, this is just terminology because now we can try and sort of write all of this in a slightly more general way. A scalar field, for example, might be the temperature at every point in the room. A vector field might be the velocity of air molecules at every point in the room. In the velocity of, for example, velocity of air molecules near the vents of the AC will be directed outward. Whereas at some other point in this room, they might have no explicit direction. It has some direction at a particular time, but that direction itself could vary in time. Maybe it's going up this time, maybe 5 minutes later it's going down, depending upon what are the flow patterns in circulation inside the room. So this is just definition of scalar field, and over here we have come up with our first scalar field. This is the density at every point in space at a particular time, or at any time t. If I fix the time t, this tells me what is rho of x. At every point x in space, this tells me what is the density. Whereas with a vector here, at every point in space, it would tell me what is the magnitude and the direction in which I am pointing. So the conventional way to draw these vectors is by little arrows. So I would have some arrow that looks like this. Okay. So this would be a vector field and this is a scalar field. Notice that when I drew these arrows, I was a little careful about how I drew them. I said if I had a vector like this, then I didn't draw a vector that was like this next to it. I drew a vector and then I said maybe the one close to it that I drew was somewhat pointed maybe roughly in the same direction but not too far away. That the reason is that there are mathematical theorems that apply to vector fields that are smooth and continuous except at isolated points. And by that I mean that between successive points, especially when I looked at the continuum limit, the direction in this arrow should not change too much. It cannot be, so I cannot have a situation where I have all up arrows here and all down, because that would be a very discontinuous situation from the point of view of the vector field. In most, or if not all examples that you will encounter, really have fields that are quite continuous. Okay, so now we're going to write that object in a slightly different way. We're going to write delta rho of x and t by delta t. So sometimes I switch notation. Sometimes I write r vector in terms of instead of x and so on. It all means the same thing. Okay, so by x I really mean positions x comma y comma z, or in general I could also call it r. Depends on what location. So this I'm going to write as first of all d del squared of rho, which is the form that we had earlier. But I'm now going to write this also as d times this operator of grad times another grad times let me just make one more step before that. If I write the vector j to be minus d times this operator which I haven't told you about yet times grad of rho, then this becomes d times del dot j with a minus sign, and I won't even have this d here. It's just a minus sign times del dot j. So I have made two steps here, and I don't want, and let me just go back and do them again carefully. I first write a new quantity, a vector here, which takes my old field rho of x and t and applies an operator called the gradient operator on that. This operator carries a vector sign, which means what is on the left is also a vector. Because always the universal way to check if your answers are right is to check that you have the same type of quantity on both sides of the equation. If there's a vector here, there must be a vector here. So this is a way of defining a vector from a scalar, in this case the density. Once with this definition, I can write this particular term here as delta rho by delta t is minus del dot j, and we just come to the meaning of each one of these terms right now. Yeah, have a question? The minus sign is by convention, and I will tell you what accounts for that. But right now there's not really a minus sign. I just put a minus sign here and a minus sign here. So I just cheated a bit, but it's just I can choose to define this in whichever way I want to. So now I can write this original equation in terms of del dot j, where j is defined here. I've just split up this equation into two parts. One is the part that says delta rho by delta t is minus del dot j, and then I must give you the definition of j. Okay. So the grad operator, this gradient, is, for example, unit vector along the x direction, delta by delta x, plus unit vector along the y direction, delta by delta y, plus unit vector along the z direction, delta by delta z. Okay? And the operator del squared is just the same as taking the del and operating on it again with another del. This is del dot del, essentially. So this, if I operate on a scalar, that object will look like a vector. So let me just show you, just give you an example of how that is. Suppose I operate the gradient operator on some function phi of x, which is the same as operating the gradient operator on some function phi, which is a function of x, y, and z. Okay? Remember that this x, now don't confuse this notation with this notation. I'm just using this as a shorthand. So then the gradient of phi is a vector which takes this phi and operates this object on that. So the first term is I times delta by delta x unit vector times phi. That is this part operating on the phi. The second part is the j vector times delta phi by delta y. That's this part operating on the phi. The third is the k vector times delta phi by delta z. Okay, so that's how I take this operator and operate it on a scalar to get a vector. So you can view this just really as a question of definition. I'm operating this del on this object j, which is now a vector, but that vector is constructed from the grad rho. And now if I imagine this going through here, this will be gradient operating upon this object here, which is just del squared operating upon rho finally. Okay, because this is del dot grad of that object operating on the right. So it's really very much the same thing. The advantage is this has some specific names. One is j is called a current. So j is a current, that's absolutely right. So it should be called a current density, j. So del dot j is this object here, delta rho by delta t. Okay. Why the minus sign, and what does that minus sign mean? The minus sign you can remember just purely from physical arguments. Suppose the density is large here and small here. So suppose on this axis I plot the density as a function of distance x. And so I just suppose I take a whole bunch of colored particles and put it in one side of some box. As these particles diffuse around, these particles will move out from where I have confined them because they're sort of moving at random. And after a long time, these particles will be uniformly spread out in that box. So although the density starting off looked like this, the density after some time will look flat. In order for this to happen, particles must move from this part of the room to this part. So they must basically be moving in this direction from left to right. Okay? They must be moving down the gradient because this gradient slope is large initially because all the particles are on this side. But as it goes on, as time goes on, it just flattens out and flattens out, which means I must take particles from here and move them to this point. So the change is proportional to the gradient. The gradient is a function that increases in this direction. The minus gradient is a function that increases in this direction. So this is the direction of the negative gradient, and this tells me that particles must move in that direction. So the current density is such that particles move in this direction, which is opposite to the direction of the slope of the density. Okay. So just remember that the gradient of phi is a vector which points in the direction where the increase of phi is the largest. The other way of thinking about it is that suppose I drew a sequence of curves where phi equal to constant, that I do a contour or a level set, whatever word I need to apply. So suppose phi is constant along here, then it's equal to another constant along all of these points, then it's equal to another constant along all of these points. Then the gradient of phi points normally to these contours, perpendicular direction to this contour, because that's where it increases the most. Okay, just again to sort of remind you of this equation written in this form, delta rho by delta t equal to minus del dot j. I don't even have to specify what j is. This is called a continuity equation. And continuity equations always express some fact of conservation. In this case, the conservation of the total number. And we'll just come back to why that's described in that manner. This other equation here, that the current J is minus d times grad of rho. This is important enough for it to have a name of its own. This is called Fick's law. That if I have a system where particles are moving with some diffusion constant, then there are currents which go down the gradient of rho, which essentially smooth out the densities, and how they do that is proportional to the diffusion constant. If the diffusion constant is very large, then the currents are large that help to smooth this out. The larger the diffusion constant, the faster all of this is going to happen. The diffusion constant is 0, there is no current. Particles don't move at all, they sit exactly where they are. So delta rho by delta t doesn't change in time. So d tells you how fast these particles are going to move through diffusion to iron out changes in the densities. For example, here it is more density here and less density to the other right hand side. Okay. So now we have understood scalar fields, vector fields. We have rewritten the diffusion equation in a form that looks like a current. We have now given that equation a name. We have said this is called a continuity equation. We have said this other way of writing the current in terms of the density is called Fick's law. And these laws were known more than 100, 150 years ago, and they were finally sort of put into logical form in terms of diffusion equations, etc., and interpreted in terms of diffusion, like more like early 1900s or so.
So when yesterday we draw one graph of diffusion, right, the probability density spreading out. In that case, the first graph with more peak, that is when t is equal to 0, right?
That's right.
Not tau equal to 0.
No, t equal. Tau is always, I will take it to be finite and then take the limit that tau becomes small. But I will never set tau exactly to 0, because then the equation that I write won't make sense. It's always in the limit that tau is vanishingly small but not 0. And that we will go back and derive that particular relation and show you where it comes from. That the graphs that I drew will tell you where they came from. Now, to actually make use of this statement, one must do a little bit more. So, for example, what I'm going to do is, I'm going to first take delta by delta t of integral of rho of x comma t dx. I'm going to imagine a big box in which I have my particles, and I'm going to integrate over this volume, the entire volume. So now I know that this is a constant, this is just the total number of particles, and delta by delta t of the total number of particles must be 0. Okay? So that is dealing with this part of the equation. Because this, we said that the integral of the density as a function of x and t at over all of x in a box where you cannot allow things to leave. If you integrate over the whole box, this quantity must be 0 because it's just, the derivative must be 0 because this is just a constant, it's just the total number of particles. All I'm saying is that the total number of particles in the box is 25 and it doesn't change in time. Therefore, if I ask the question, what is the number of particles in the box, and then I ask the question, how does that number change? The answer is 0 because it doesn't change. That's just expressed in this particular form. Okay? So to mathematically, I can put a d by dt here because this quantity, once I do the integral, is a function only of t. So there is no partial derivative. If I want to take it inside, then I write it delta by delta t. So now I want to ask, what happens when I do the integral over the whole volume dx times del dot j. I can put the minus sign also, it doesn't really matter to me. Okay? So I'm integrating the del dot j over the whole volume, this whole box that I have here. So now I will state without proof that the answer is minus integral over the surface, over the full surface, the closed surface bounding that volume of j vector dot ds. So let me explain each part of that. This is called the divergence theorem, and if you have not seen it, don't worry too much about it. It's a very standard theorem in sort of vector analysis or vector calculus, which says that this integral equals this integral. Okay? How many of you have seen this before? You haven't seen. Don't worry too much about it. If I can sort of, if you can look it up and see what it does. Right now I just want to worry about the interpretation of this. Roughly speaking, what del dot j does, or del dot let me say j is that if I have a vector that is doing something like this, it's sort of diverging from a point. That's where the origin of the word divergence comes from. Then this quantity del dot j measures how exactly it's moving away from that point, roughly speaking. You can convince yourself of that by taking an actual example of this. So this says that if I look at all the divergence inside this whole volume of this j, then just by knowing what j is doing on the boundaries, what is doing on this surface, doing on this surface, doing on this surface, etc., I can find out the behavior. This integral really is the same as this integral. Okay. This is a statement about j in the volume. This is a statement about j on the surface. So j, we said, was a current density. Now here, if we do not allow any particle to leave here, there can be no current at the surface. There is nothing going out versus going in. Alright. Therefore, this particular integral here must be 0, just as a consequence of the fact that this was 0. If particles were allowed to leave, then this integral would be non-zero because there would be a current across the surface. But over here, because there is nothing is allowed to leave, there can be no current across the surface. Therefore, this must also equal 0, just like that. This is dx. This is, so the notation is integral dx here is the same as integral, what you sometimes say dv, integral over a small volume. That is, this is really the same notation between these. You can I don't want you to be confused by the notation, which is also the same as integral dx, dy, dz. I can write it in any one of these three forms.
But this volume element is that vector?
No, the volume element is, okay, I understand your confusion. The volume element is a scalar. So that's a good question. So I've written it with an x to say that what I mean is this combination x, y and z, but this volume element is actually a scalar volume element.
The dx vector which we used before was a different one, right?
So all of this is just a scalar volume element. Whenever I use dx, that's always a scalar volume element, like that dv that I have written. On the other hand, this is a vector element. And what this means is, I have a surface like this. I break up the surface into small infinitesimal units of surface, and this each of them have area, say, let us say ds, and the vector ds with a vector on top of it is this amount of area times a unit vector n hat from the inside to the outside. Okay, so ds vector is the same as the magnitude of this infinitesimal element times the n hat vector at that particular point. The reason I need to do this is that j is a vector. So look at this little surface again. J is a vector. J might be pointing in this direction. It has to be dotted with another vector, in this case the n hat vector, in order to give you something sensible, which is a scalar function on the right hand side. Look again, so let me just go back to saying j is this particular quantity. There are other ways of writing j. Suppose, for example, I have a bunch of particles here. This is some density rho. Suppose these particles are moving with some velocity. There's a local velocity field v at x and t. So this is v. So an alternative equation for the current in such a situation where particles are moving with some velocity, the point x, is just rho times v at x and t, where this v has a vector. This is not the same as what I wrote here, because here particles have velocities. The point about diffusion is particles don't have net velocity, they're sort of wandering around like this. It doesn't make sense to talk about the velocity of a diffusing particle. I can talk about its position. But if I have things that move with certain velocities, the current j can be written as the density times that velocity. So del dot j is a scalar. It's integrated over with respect to a scalar quantity, which is the volume dv. So this object is a scalar. ds is a vector because it's a little surface times a unit vector here. So it's scalar times a unit vector here. The j dot ds is now a scalar. So both quantities on the right and left are scalars. We didn't do del dot phi, we did del phi. Phi is a scalar. So the gradient of a scalar is a vector. So grad phi is a vector. But if I want to operate the gradient operator, the del operator, on a vector, that gives me a scalar. So let me just summarize that here. If I have gradient with a vector sign on it operating on some scalar function phi, this gives me a vector. If I have a gradient operator operating on a vector here, this gives me a scalar. And the operation on the vector is denoted by this dot, a dot product. So, a slightly more formal way of writing it is that this is delta j x by delta x plus delta j y component by delta y plus delta j z component by delta z. It's the same as this thing, which is the sum of three scalar terms. So the usefulness of writing it in this form is here, if we don't worry about the full box, but if we only worry about a small volume inside that box, suppose I'm just looking at a tiny little volume inside here. So I can count the number of particles inside that volume. That's just the integral of the density across that volume. So suppose this little volume here is some delta of V. And by integrating delta of V over this little volume dx, rho of x comma t, this is the number of particles in that volume at time t. Okay. But now if it's not the whole box that I'm worried about, but only a little sub-volume inside that box, then this quantity can change in time. Okay. Just as we said that if we had a large density here and a small density here, after some time it became flat and uniform, which meant that suppose I had sat in a little box here at this value of x, looked at a little box in the density here, that density in that number of particles in that box would go down because I'm spreading those particles out more uniformly. Okay? So this number of particles in that volume at time t, this certainly will depend upon t. So there's a meaning to which I can assign d by dt of the integral of a small volume delta V dx rho of x comma t. That's his meaning, and this is not zero in general. But now we can do the same trick that we did earlier, which is relate this particular quantity to the del dot j. Okay, so delta, if I take this inside here, this becomes integral delta V dx delta by delta t of rho of x comma t. Okay. So then this becomes an integral over delta V dx, but now I can go back to the continuity equation. Then what I have is this is minus del dot j. All I have done is this is here. Instead of that, I have just substituted this here. And all of this other part remains the same. But now I can simplify this even further. This becomes an integral over the surface bounding that little volume, that little delta S bounding that little volume, minus sign outside, j dot ds. Okay, I have just used the same old trick that I wrote here as the divergence theorem. Okay, so this is the current calculated over the whole surface. This quantity need not be zero, but what it's telling you is if I have particles here, the only way the density in this can change if particles leave the surface. So I only need to know what is the current at the surface in order to integrate this quantity and equate that to the particle loss from inside. Within the little box. This is now a local statement. Within the big box, explicitly nothing could leave the box, so therefore this integral had to be zero. I'm saying I can go a little further with an equation like this, because these are equations that apply at a particular point x and t, both on the left and right hand side. They're local statements. What that means is I can also ask what are the implications of that for small little volumes inside. They don't have to occupy the whole box. So this implication is that something that is inside this little small test volume can only leave through the surface. It can't be created or destroyed inside, because delta, the total change in the density, total change in the number, can only come because these particles are leaving the surface with a certain vector current j. Which is why this is called a continuity equation, because this expresses the fact that the number of particles are conserved not globally but locally. This is an important point, because suppose I said n is number of particles is constant. In principle, I could have destroyed one particle here and created it very far away. So then if I looked at the system, it would look as though the number of particles was always the same. But that's not a local statement, because I've done something very non-local. I've killed it here, I've destroyed it here and created it somewhere else. But this equation is a powerful statement because it says density must be conserved locally. So the density in a particular region can only change if particles in that region leave through the boundaries of that region. And the way to calculate that is to calculate the current of particles, multiply by take the dot product with the little surface element of whatever funny surface that you're considering, and sum over the whole surface in order to do that. Is that clear? Are we clear with that? So here again are our two basic equations, the conservation law as expressed in the continuity equation, and Fick's law, which tells you how density gradients, what is the current associated with density gradients. If there are no gradients at all, then the current vanishes altogether. If particles move with some net velocity, then I also showed you how to define the current. The current J, if I had a certain density of particles, rho at point x at time t, with some velocity v at point x at time t, this is a way of defining current in that case. Okay, so you can see that this differs a little bit from the definition of J in this case. It's not a global equation, it's a local equation because it applies only at one particular point x. Global equations are statements about all of x in a whole volume. But the sort of miracle of this is that we have been able to write these equations completely as local equations, which have the interpretation that you conserve particle number locally. You do not create or destroy particles locally, they can only leave.
Move out of the small volumes.
That they can, but you can keep track of that by looking at the current crossing the surface. So the change in the density, change in the number inside is proportional to the number that are leaving this thing per unit time. Okay, so the change in the number per unit time is the number leaving per unit.
Yeah, but then you are saying that in the whole volume the particle is the same, right? That's why.
In the whole volume, yes, that's because, but that
is global.
That is global, but right now we're making only a local statement. So it's true, whatever particle leaves here must enter in another volume here, whatever reaches here must enter another volume here. This other volume can send particles inside. But once I look at the whole box here, nothing can leave that box. So that is a global statement, that the total number of particles in the box is globally constant and conserved. This is the local statement that says that particles inside here number of particles inside any volume can change, any subvolume can change, but it can only change when particles leave or enter through the surface. Okay. Let me just go back to one thing that we did earlier, which is, remember that we had said, let's derive the important feature of the random box, which was basically that the quantity delta squared average was a squared times n. So remember how we did that. We said, let's just imagine that you take any, suppose this is the origin, 0. I'm at some point r. R is made up by taking a times some unit first step plus a times some unit second step plus a times some unit third step, etc., etc., etc. Then we calculated r squared, and then we averaged, and then we said the only term that contribute are a squared times e1 hat dot e1 hat plus a squared times e2 hat dot e2 hat, etc., etc., because all the cross terms vanished when you average. So then we said that this was n times a squared, and then we said r squared equal to n average equal to n times a squared is a very important result in random walks. And we we did this in multiple ways, but here was one very simple way of answering the same question. Okay, so now let me just write it in a slightly different way. So remember that n is the number of steps. If I'm allowed to walk for a time t, and every time step tau I take a step, then n must be the total time I take divided by the number of steps tau. Okay. Now remember that the diffusion constant d was defined as a squared divided by twice the dimension times tau. Correct? So now I can put that back and write in for n I substitute t divided by tau, and for tau I substitute, so let me just write that again, r squared average is n, which is t divided by tau, times a squared, which is t divided by tau is a squared divided by 2 dd, right? Which is twice d divided by a squared times t times a squared again. So this is times a squared, which is 2d dt. Okay. So all I've done is just make various substitutions, but now this equation here has the same interpretation as this equation here, except that now it's written in terms of the continuous time, because now I've taken tau going to 0, a going to 0, in such a way that an equation like this makes sense. So this again is a fundamental law of diffusion. It's no different from this, but this is a probability of the probability distribution of R, because this quantity on the left here is what is the probability of being at location R at time t, given that you started at some location 0 at point 0. Integrate over all values of R, so integrate over dr and multiply this by R squared. This is the average value of R squared. So therefore, if I calculate this particular quantity, from here calculate this integral, then I should get back to this answer. That's what we'll have to try and see how we do that. In fact, the whole thrust of our argument will be, how do you calculate P of RT given 0, 0, or P of x, t given 0, 0. We've already done one thing. We have said what is the equation that P of xt satisfies. We haven't solved that equation. We have found out that that equation is a diffusion equation. So the solution of that equation should tell me what is P of x, t given 0, 0. Once I have that solution, I can calculate any property that I want to, any function of x, the average value. In particular, I can calculate this quantity and get R square average, and then I should get back to this answer. So all of this is an internal check on this whole sequence of ideas.
Why have we taken the magnitude of R? Like R mod would be the magnitude?
That's just in a sense notation. R is a vector. So R dot R is a scalar. And what R dot R is really the magnitude of R vector squared. All of this is the same as this. So then sometimes I prefer to write it as mod R squared average, because this, or I can just forget about the vector. In order to convince myself it's not a vector, I've dropped the vector sign here and written just R squared. I'm just being slightly sort of careless about exact notation, but I hope you'll follow the argument of how we got here. Okay? So now the question is, let us now take this equation. Let's just first do it in one dimension. Delta P of x, t by delta t is d times delta squared by delta x squared times P of x, t. And always remember that P of x, t carries information of where you started out with. The P of xt will be different if I start out at site 500 kilometers away from the origin as it is when I start from the origin. So this information about my initial condition must be hidden. The 0, 0 is starting at 0 at time 0, but in general I could have starting at some other point at time t equal to 0, or I can have some probability distribution that determines where I am at time t equal to 0. All of this I can put in and should go into influencing that answer. Okay? So now we'd like to solve that equation. In order to solve it, what we need to do is something called a Fourier transform. And I'll just tell you exactly what that is. There's no particular mystery to it. If I have some function, first of all, let's start with the Fourier series. Suppose I have some function f of x let me say I define it in some interval, say between minus L and L, some function inside there. That function, I can choose a very simple function. That function might be some function that looks like this, which is a sine wave. So then I would say that f of x is some amplitude of the wave times sine of k times x. And k is 2 pi divided by lambda, where lambda would be the wavelength of this. That's the simplest way of saying this. Okay. So now, by telling you what a is and what k is, I have told you exactly what this function does. So I've said I don't have. I've said that of all the possible wavelengths that this wave can take, choose a particular wavelength, lambda, and choose a particular amplitude, and that's all I need. I don't have to tell you about the function every point that value that function takes here. In general, if I could think of a more complicated function, which is say a function that looked like this, and then I would say that this function I can break up as there's a contribution from a wave that looks like this, there's a contribution from a wave that looks like this, there's a contribution from a wave that looks like this. It's just adding up different waves, I can reconstitute that function. Okay. So the other way of writing it is that f of x is just some summation over a set of coefficients n equal to 0 to infinity. Here is the value of that coefficient, and then I have something like cos of kn x plus bn sine of kn x. This is if I add a sufficient set of causes and sines. So kn here would be 2 pi n divided by some lambda wavelength, and this is just saying that I can make any function I want by just adding an appropriate number of functions that are perfectly periodic. This is just a very practical way of approaching the whole question of what are Fourier transforms and Fourier series and so on. So this might be called a Fourier series representation of a function. And the Fourier transform is just a little more grown up version of a Fourier series. So that was just the motivation for doing it. I can now actually write down a Fourier transform by saying the Fourier transform of a function f of x is defined as the integral over a set of values k e to the power I kx times another function f of k. And the way to go back to f of k is f of k is 1 over 2 pi integral. So these integrals all go from minus infinity to plus infinity dx e to the power minus I kx times f of x. So f of x and f of k are what are called Fourier transforms of each other, or Fourier transform pairs. So what the Fourier transform does is essentially generalize the idea of a Fourier series to a case where you can have an infinite sort of spread in the range, in the domain of the function. So I could have some function that looked like this, where this was minus infinity, this was plus infinity, and I can take this and again make it the sort of waves that I did over there. This is just a more general way of decomposing it into a bunch of waves. The e to the I kx is cos kx plus I sin kx. I'm just writing it. I mean, we just sort of derive what use this actually is. But remember that from f of x, I can go to f of k. From f of k, I can go back to f of x following these rules. So one simple way of checking this is actually to check that it works. So for example, for f of x must equal integral minus infinity to infinity dk e to the power I kx times f of k. But now I know what f of k is, so I can just take this, substitute in there. All right. and if x is obtained by an integral over k, k is obtained by an integral over x. This is a dummy variable because it doesn't matter what I call this variable. Finally, there's no trace of this. It's all going to be integrated over. So I can equally well write it as integral minus infinity to infinity, put the factor of 1 over 2 pi over here, write this as dx prime e to the power minus I k x prime f of x prime, because it's just a dummy, as I said. All right. Now I'm going to do another trick, which is to interchange this integral with this integral, which I can always do. So then I will write this as integral minus infinity to infinity dx prime. Okay. Then the second integral is, there's a factor of 2 pi which I can also pull out here. I can grab that and push it to this side. I can write an integral minus infinity to infinity dk e to the power I x minus x prime times k. I've taken this, combined it with this, put it all to the right, because both of these carry the k which is being integrated over. And finally, I have an f of x prime sitting here. You will agree that this is the same as this. All I've done is change the order of integration, pull out this exponential and write it in this particular form, and then simplify it in this way. But now it's even simpler, because this f of x prime, I can also pull that out, because this is dk, k appears here, but this f of x prime is not integrated over at all. So this is really the same as the integral minus infinity to infinity 1 over 2 pi sitting outside d of x prime into f of x prime integral minus infinity to infinity d of k e to the power I k times x minus x prime. Okay. Now this particular integral is actually known. Integral minus infinity to infinity dk e to the power I k times x minus x prime is a function which is 2 pi times a delta function of x minus x prime. The delta function is a very interesting function. It's 0 almost everywhere except when x equal to x prime. So what it does is it just picks out only that value of x prime which equals x for you. Otherwise, anywhere else it's 0, where x is not equal to x prime. So now we can put that back in here and see the 2 pi and the 2 pi will cancel. What I will have is an integral minus infinity to infinity d x prime f of x prime times this miraculous delta function x minus x prime. So what is the rule? Wherever I have an x prime, I set it equal to x. So then, this using the fact that integral minus infinity to infinity dx has to be 1. Okay, this quantity is just f of x. So f of x equal to f of x that I started out with. So this is a complete and consistent definition. That if I take it and I Fourier transform it first forward and then backward, I get back the original function that I started out with. We might want to think about this a little bit so that you're sure. There are some ingredients that went into this. First of all, there is this particular ingredient that went into this. The second ingredient that went into it is the definitions of the Fourier transform and the inverse Fourier transform, the ones here. But with this and this, we can go from an object, from a function f defined in the space of x to a function f defined in the space of k. These are different functions. So technically speaking, I might even put a f hat over here to be really, these are not the same function with just a different variable inside. They could be different functions, but they're related by this process of transformation from one to the other. And the way, if I go from f of x to f hat of k, I can go back here and regenerate my f of x. That's really what this is showing. If this is a bit advanced, don't worry about it, because we will only use this to do a particular calculation.
Can we conclude from that step directly to f of x because of that a is equal to 1?
Which one?
In the last two steps.
Yeah.
The the dummy variable d of x bar is there and delta of x minus x bar is there.
Yeah.
So we have to say that by multiplying that impulse or delta function with f of x and then integrating it, we get fx, right?
That's right. So this says that essentially the delta function really makes sense only when you integrate over them. So if x, suppose I say I'm going to integrate over some region here. Suppose this is x prime. Suppose this is x and this is some region I'm integrating over. If this region does not include this point x, then the answer is 0. But by integrating from minus infinity to infinity, I've ensured that somewhere along that interval, I've included the point x. Only at that point does that integral become non-zero. Because of that, it picks out that value. Everywhere there is x prime, I can put x inside once I do the integral. So this is called, there's this property called the sifting property of delta function, which is whatever the function is, it extracts one particular point from you. So for example, if I had a function, to give you an example, if I had a function f of x, I multiply this by delta function of x minus a, and I integrate it over all x, what I would have here is f at that particular point a. That's exactly what the delta function does for you. It grabs this point and pulls it out for you. So if you're interested in the value of a function at a particular point f of a, one way of writing it is to say, I'm going to multiply it by a delta function which picks out for me that particular point a and do it via this integral. Okay. So when I go a little further in the next time, which is to actually show you how to use this to very simply and easily derive the solution of the diffusion equation and understand and interpret what it means, then this will become a little clearer and you won't be. But you should look upon this at least very practically, not as a complicated mathematical tool, but these are tricks and ways of getting answers. And rather than get drowned in the mathematical subtleties of what you can Fourier transform and what you cannot Fourier transform, let's just be very practical about it, define this and show you how to use it in a particular context. Okay? All right.